We introduce AMS, a novel augmented mass-spring scheme for real-time simulation of dense hair at the strand level. Our approach considers the traditional edge, bending, and torsional degrees of freedom in mass-spring systems, but incorporates an additional one-way biphasic coupling with a ghost rest shape configuration, which enables us to model each strand using a low number of particles and results in a strictly heptadiagonal system matrix. The first component of our biphasic model is an angular spring, whose force is proportional to the angle deviation from the ghost rest shape configuration. This design increases system stability, even under high tension in edge, bending, and torsion modes. Additionally, we introduce a distance-based integrity spring, which alleviates sagging effects and helps preserve global geometric features. Note that in traditional mass-spring systems, sagging and shape loss can only be mitigated by applying increasingly large tension magnitudes, which eventually lead to system instability. We evaluate our model's fidelity by comparing it with a hybrid Kosarat MPM simulation using the same hair asset and wind environment. In contrast to previous state-of-the-art, our method is able to simulate the entire hair asset with thousands of strands in real time and requires no additional pre-processing to prevent sagging artifacts. More complex hair simulation frameworks often use interpolation methods like LHS to generate dense hairstyles from a few guide strands, reducing computational costs. However, this often introduces artifacts during object interactions. We also compare against a neural-based interpolation method. While it increases strand count, the neural method relies heavily on training data and produces artifacts when handling new head poses or objects in the scene. Our model captures the behavior of different hair types, such as the increased stiffness of shorter strands. This enables higher fidelity simulation of diverse assets, including asymmetric styles and facial hair. In contrast, traditional mass-spring systems treat all strands uniformly, regardless of length. Moreover, we parameterize a non-linear Hookean response in the integrity spring, allowing our model to capture the gradual loss of global shape under extreme forces, such as those experienced on a roller coaster. In this simulation, we compare the scrambling effect and progressive hairstyle deformation for different types of hair. Finally, we showcase a range of applications enabled by our real-time dense hair simulation framework. It can manage complex hairstyles under highly dynamic conditions, making it ideal for animation, character performance, and cinematic rendering. It also allows real-time strand-level editing, letting artists physically interact with and reshape dense hair directly. And it supports live control of digital avatars through camera input, capturing subtle head movements and delivering high-fidelity, responsive hair motion. Thank you for your interest in our work and watching this video.